Hello everyone, I am Nitin Reddy from EC and my topic is an overview of terahertz antennas. Abstract. The terahertz antennas, which have features of small size, wide frequency bandwidth, and high data rate, are important devices for transmitting and receiving terahertz electromagnetic waves in the emerging terahertz systems. However, most of terahertz antennas suffer from relatively high loss and low fabrication precision due to their small sizes in high frequency bands of terahertz waves. Therefore, this paper presents a detailed overview of the most recent research on the performance improvement of terahertz antennas. Firstly, the development of terahertz antennas is briefly reviewed and the basic design ideas of terahertz antennas are introduced. Then terahertz antennas are categorized as metallic antennas, dielectric antennas, and new material antennas. After that, the latest research progress in terahertz photoconductive antennas, terahertz RN antennas, terahertz lens antennas, and terahertz microstrip antennas and terahertz and chip antennas are discussed. In particular, the practical difficulties for the development of terahertz antennas are discussed with promising approaches. In addition, this paper also presents a short review of the progress technology of terahertz antennas. Finally, the vital challenges and the future research directions for terahertz antennas are presented. Development of terahertz antennas. In order to facilitate readers' understanding, we briefly describe the development of terahertz antennas in this session. Then the design ideas of the terahertz antennas are discussed. Although the study of terahertz began in the 19th century, it was not studied as an independent field at that time. Most of the studies related to terahertz belongs to far infrared region. It was not until the middle and late 20th century that researchers began to advance millimeter wave research into terahertz band and established specialized research on terahertz technology. The emergence of terahertz radiation source made it possible for terahertz waves to be applied in practical systems during the 1980s. The development of terahertz technology. Since the beginning of the 21st century, wireless communications technology has developed rapidly, and the demand for information and the increase of communication equipment have put more stringent requirements on the transmission rate of communication data. Therefore, one of the challenges of future communication technologies is to operate at a high data rate of gigabits per second in one location. Basic terahertz antennas. Terahertz antennas have many available types. Pyramidal cavity with dipole angle reflector array bowtie dipole. Dielectric lens planar antennas, photoconductive antennas for generating terahertz source radiation sources, terahertz RN antennas, terahertz antennas based on graphene materials, etc. Based on the manufacturing material of terahertz antennas, they can be roughly classified into metallic antennas, dielectric antennas, and new material antennas. First one, metallic antennas. Horn antennas are one of the typical metallic antennas, and the horn is designed as an antenna operating at the terahertz band. The antennas of the classic millimeter wave receiver is a conical horn. The corrugated and dual mode antennas have many advantages, including a rotationally symmetric radiation pattern, a high gain of 20 to 30 dB, and a low cross polarization level of 30 dB with 97% to 98% coupling efficiency. The available bandwidth of the two antennas are about 30% to 40% and 6% to 8% respectively. Since the frequency of terahertz wave is very high, the size of the errant antenna is very small, which makes the processing of the tip end of the errant difficult, especially in the design of antennas arrays. And the complexity of the process technique leads to high cost and limited production. Due to the difficulty in manufacturing the bottom of the complex iron design, a simple iron antenna in the form of tapered or conical iron is usually used, which can reduce the cost and process complexity, and the radiation performance of antenna can be kept good. Another metallic antenna is a traveling wave corner cube antenna consisting of a traveling wave antenna integrated on a 1.2 micron dielectric film suspended in a longitudinal cavity on a silicon wafer, as shown in figure 8. This antenna is an open structure that is compatible with Schottky diodes due to its relatively simple structure and a low manufacturing requirements. It can generally be used in frequency bands of above 0.6 terahertz. However, the antenna's side lobe level and cross polarization level are higher, probably because of its own structure. Thus, its coupling efficiency is relatively low, about 50%. The second one is dielectric antennas. The dielectric antennas are the combination of dielectric substrate and antennas radiator. By proper design, the dielectric antennas can achieve impedance matching with the detector and have the advantages of simple process, easy integration, and low cost. In recent years, researchers designed several narrowband and wideband edge-emitting antennas that can be matched to low impedance detectors for terahertz dielectric antennas. Butterfly antennas, dual U-shaped antennas, algorithmic periodic antennas, and log period sinusoidal antennas as shown in figure 9. In addition, more complex bent wire antenna geometrics can be designed by means of a genetic algorithm. However, since the dielectric antennas are combined with dielectric substrate, surface wave effect is generated when the frequency tends to the terahertz band. This fatal disadvantage causes a large amount of energy loss during operation and results in a significant decrease in antenna radiation efficiency. As shown in figure 10, when the antenna radiation angle is greater than the cutoff angle, its energy is trapped in the dielectric substrate and coupled with the substrate mode. As the thickness of substrate increases, the higher order modes in the substrate also increase. However, these higher order modes are repeatedly radiated in the substrate and the energy radiated by the antennas is coupled. With increasing high order modes, the coupling efficiency between the antennas and the substrate medium is increased. The situation results in the energy loss. To weaken the surface wave effect, there are three optimization schemes. Loading the lens on the antennas, the antenna bunching property is used to increase the gain, reducing the thickness of the substrate. The high order mode generation of electromagnetic waves is suppressed, replacing the substrate dielectric material with electromagnetic band gap. The spatial filtering characteristics of EBG can reduce high order modes. Third one is new material antennas. In addition to the above two types of antennas, there is other kind of threads antenna made of new materials. For example, in 2006, Chin proposed a carbon nanotube dipole antenna. This dipole is made of carbon nanotube instead of material. The general antenna characteristics of finite length carbon nanotube dipoles, such as input impedance, current distribution, gain efficiency, and radiation mode, are discussed. The curve of input impedance of carbon nanotube dipole antennas versus frequency. At the higher frequency band, the imaginary part of the input impedance has multiple zero points. It shows that the antennas can realize multiple resonance points with different frequencies. Obviously, the carbon nanotube antenna exhibits resonance with the certain frequency range, while is strongly damped outside of this range. Conclusion. With the development trend of wireless communications, future spectrum resources are moving to the terahertz band, and the establishment of a terahertz wireless communication system can provide a higher data transmission rate. Terahertz antennas are important devices for transmitting and receiving terahertz using communication system. Meanwhile, the performance of terahertz antennas has a great influence on communication system quality. This paper carried out in-depth analysis of terahertz antennas, including research background, basic concept, typical terahertz antennas, and process techniques. Through analysis, it can be found that terahertz antennas currently encounter high cost, low gain, and other challenges. Most of the terahertz antennas are still in the theoretical stage, and the practical products are rarely manufactured. Obviously, the future research task of the terahertz antennas is very heavy. We proposed key research directions as follows. improving the antenna geometry to achieve manage maturation, optimizing the radiation performance of the antennas to achieve high gain, adding encryption technology to achieve high reliability, using appropriate packaging technologies to improve the integration of turrets antennas. Thank you.